check my voice.
Now she projects. Let me get the
Okay, so here's the question. What is the structure of the universe on the largest of scales? Okay, simple question.
Excuse me. I'm only seeing, oh no, I'm sorry, my fault. Forgive me. You're good.
Okay. So here's an analog. Picture a colony of ants living at the base of the Empire State Building, and they want to make a map of planet Earth. They know there is a planet Earth. They want to make a planet Earth. This analog is an analog only conceptually because the scales are completely off. The ratio of the size of an ant to planet Earth is 10 to the 10 billion. The ratio of a human being to the visible universe is 10 to the 25. So there are 15 orders of magnitude difference. But conceptually, this is understandable. Okay, so what is the answer? We don't really know. We've made progress, and it's all been in the last 100 years. But if someone tells you that we understand the universe, don't believe them. It's not true. Okay, so here's the history of what we've learned. Starting about 100 years ago, 1927, George Lemaitre proposed the Big Bang cosmology, that the universe started with a primordial atom and there was an explosion, and that explosion has been going on ever since. And 2 years later, Edwin Hubble confirmed that by basically mapping the homologous expansion of galaxies. Homologous meaning the speed is proportional to distance, which is the signature of an explosion. In 1940, George Gamow came out, he's a nuclear physicist, with Big Bang's nucleosynthesis, where he showed that based on what we know about the different elements, the different nuclei, and the temperature of this explosion, that the abundances of the elements created by that process is consistent with what the universe has. Basically, mostly hydrogen, a little bit of helium, and then very small amounts of everything else. Well, the heavy elements are made in stars, as we know. Okay, so here's these ants. We look around the sky. What do we see? You see lots of stars, 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 stars. We see the Milky Way, and we see a large asymmetry of galaxies from the northern sky versus the southern sky. And this is dominated by this cluster known as the Virgo cluster because it sits in Virgo. So what have we learned so far? Okay, here is the solar system. This is the sun and all the planets in a area in a light of about 5 light hours. That's the orbit of Pluto. But it's embedded in this large cloud, which is about a light year across, and it's called the Oort cloud. And I had the great pleasure of taking Jan Oort to lunch in 1978, an amazing man with lots and lots of stories. So we know that this cloud contains lots of remnants of the formation of the solar system. Okay, so all of the big pieces that come into the system come out of the Oort cloud. Okay, so we now move out a little bit, and we're looking at our galaxy, and here's the arms of the galaxy. And there is an arm called the Orion arm because it contains Orion, and the sun is embedded into the third arm of our galaxy. We can ask questions anytime. There's the galaxy. Here is the Orion arm. You notice the scale. So the scale is now getting fairly large, about 80,000 light years across. That's a fairly big size. And now we move on to a scale. Big fingers. So there is a scale, almost a million light years, of what we call the inner local group. The galaxy, the Magellanic Cloud, Sculptor, Eta Carina, Sextans. So it's a group of about a dozen gravitationally bound. So they are stuck together. They're moving around in orbits. They're not true orbits because it's not a two-body system. It's like a gas of galaxies. Here is a larger picture of the local group. So here we are. Here is galaxies that come in all sizes and shapes. There's about 80 galaxies in the local group. Most of them are dwarfs, but there's a couple of large spirals. They are gravitationally bound. So this group is held together by gravity. There's a bigger blow up. Maybe you can read some of the names of the galaxies. You have M31. I can't read it. It's out of focus. There's NGC 300. But this picture is meant to be a three-dimensional picture. That's why it's dropping down so you can see, try to get an understanding of 3D. It's a picture constructed from somebody far away, making a three-dimensional image. Okay, so here's this local group, and there are other local groups that are nearby. Near is a relative term, obviously. The Virgo cluster, which has about 2,000 galaxies in it, is 65 million light years away. Okay. Draco, 40 million. Smaller group, about 15 galaxies. Here's the Leo group, M66, about 30 galaxies, 38 million light years away. M81 group, the M81 group, relatively close at 11 million light years away. And Ursa Major group, a group of about 30 galaxies, about 55 million years ago. There are other groups, other smaller groups. Yes, the local group. So it does not have a name. It's just called the local group. Here is Virgo, a magnificent picture dominated by M87. And that M87 is, I'm sure you've looked at it before. Here's what I call the silkworm constellation. That's not its name. It has a name. I forgot what it's called. But there's a total of about 2,000 galaxies in this cluster. And it is gravitationally bound. So these 2,000 galaxies are moving around in random orbits like a gas. So these are particles in a gas. And if you measure the random velocity dispersion, it gives you an indication of the total mass. And at this point, when people started to do this in the late 70s, they came up with a problem. The problem is that the velocity dispersion is inconsistent with the amount of mass if you look at the light. And therefore, there must be something that's dark, and this is the source of the dark matter problem. Okay, I don't want to get on that road, but there are other alternatives to the dark matter problem. But according to the consensus at the time was that the light accounts for about 5 or 10%, and 90% of the mass is unseen, dark. Now, what is that mass? All sorts of stupid things have been hypothesized. We don't know, and we will probably never know. Here are the names of some of these guys. There's the center, which is M87, M84, 66, M88, M89, M90. And These are fairly bright galaxies, so people put telescopes on them and take a look. So we now move on from the Virgo cluster, these 2,000 galaxies, of which we are part, into what is called the supercluster. The Virgo supercluster has about 10,000 galaxies. This is the Virgo cluster itself, and these are all gravitationally bound clusters, but the whole system, which is on a scale of 300 million light years, very big, is not gravitationally bound. So these groups are sitting around being spread open by the Hubble expansion.
One question.
Yeah.
Where are we there in that Virgo cluster?
Where are we? We are, too many buttons. We are, not working anymore, the battery there?
Yeah, it's working. Battery.
Changes light? Yeah.
Yeah, it's on.
So this is Virgo, and we are like here. Okay? Okay. So here is the Virgo cluster with some names. So here's Virgo, Ursa Major, Leo Group, Eridanus, Fornax. So remember the scale here. The scale is huge. 300 million light years. Again, to visualize in 3 dimensions, normally you rotate this image on a TV screen and you can see, but you get the idea. Okay, in the sky, if you look at all of those small clusters and map them, they all kind of map here in the southern hemisphere. Here's Virgo cluster by itself. It's very dominant in the sky. Everybody can see it clearly if you got a small telescope. And all these other guys are here because they're relatively close. So the angles is large. So this is the Virgo supercluster. Okay. A word about homologous expansion and the Hubble constant. So we have been measuring the speed at which galaxies recede from us since Hubble in 1929, and we have made a measurement of that number, which is the slope of this line, and it's on the order of 70 kilometers per second per megaparsec. Astronomers like to talk in parsecs. That's 21 million light years. So the slope of this line tells you that if you see a galaxy and you're able to measure the distance, and we do that by looking at variable stars, I'm sure you know that, there are stars that blink and the blink rate is proportional to their light, and you measure the magnitude, and you can calculate the distance. This is how we get it. So we know this very accurately. And we have to talk about the microwave radiation now because it's a key issue. So, in 1948, there was a hypothesis of the existence of a cosmic background radiation by Ralph Alpher and Robert Herman. And working with George Gamow again, they predicted the expansion of the universe from this hot primordial atom. And if you believe in nuclear physics, you know that at some point that hot matter radiation had to be in balance. And as it expands, things start to condense out, nuclei condense out, but the radiation also cools. So you have these photons in this bubble that's expanding, and it's getting cooler and cooler and cooler. And in 1964, Arnold Penzias and Robert Wilson, working for Bell Telescope, Bell, they were able to measure the existence of this radiation because they had built this giant microwave horn antenna that could point anywhere in the sky. And they started pointing it. And I don't know if you know the story, but there was always a residual hiss, so they could never get it down. And one of the students noticed that there was a lot of bird droppings in the antenna. So they figured, oh, it's the dielectrics of the bird poop that's making the noise, and they cleaned that out. Nothing changed. And eventually they realized it's real radiation coming from space, and it's uniform across the sky. That was the discovery of the microwave background. And the technology got better and better. So this is the original work. This is the original work in 1965. By 1992, we had satellites which were measuring at a much higher angular resolution. 2003, WMAP gave us a really, really high detail, which lets us make arguments about stellar evolution, galactic evolution. Anyway, that's another subject. We know that from theory, this background radiation has to be black body, that is thermal Planck radiation, and it has been verified to a very, very high degree. Its temperature is 7.255 kelvins. Amazing the accuracy. An interesting point is that 20, 30 years before this, a radio astronomer, Canadian radio astronomer, noticed that all the molecules that he was focusing on, he was tuning into various molecules, were all at an elevated temperature, about 3 degrees. He made the first measurement of the cosmic background radiation, but didn't know it. Okay, but it's in his book. And someone, after this was discovered, went back and say, oh yes, the measurement was made. Interesting aside. Okay, so you picture the universe as a big ball, because you can't picture it anywhere else. The radiation inside is at rest to the ball because it's moving around at the speed of light. And therefore, anything moving inside there will have a blue shift or a red shift, depending which way it's going. So once we had the very high accuracy measurements, we were able to determine that we, meaning planet Earth, has a velocity in one direction, which is towards, and one direction, which is further away. The work was done in 1969. It's called the dipole, cosmic background dipole. And the significance of that, here it is on the sky. This is where the dipole is aiming. This is where we and the solar system, the sun, is moving towards. Fairly close, suspiciously close to the Virgo cluster. But remember, the Virgo cluster has a lot of mass down here, so the point is shifted. So we're moving towards this point and away from this point at a speed of about 370 kilometers per second. Relatively small sign. So the question is, why? Oh, cool. So if you take the Hubble constant to be 70, which we know 70 kilometers per second per megaparsec, we know the distance to the Virgo cluster, and we should be moving away at 1,395 kilometers per second. But we're not. We're moving away at 1,024. The difference, this 371 kilometers per second, is the number that you get from the background radiation dipole. So the question is, why? And the answer is simple. We're sitting next to 2,000 galaxies, which have an enormous mass, and they've been pulling the local group into it because we are part of it. So over the age of the universe, this 370 kilometers per second has basically been the acceleration due to the gravity pull of the Virgo cluster on our local group. Okay, so in 1970s, again, when a lot of this work was being done, the idea of the great attractor appeared. Great attractor, the region of gravitational attraction centered on 14 hours, 20 minutes, minus 62 degrees. Okay, so it's in the southern hemisphere. It was mapped by Harvard and lots of other organizations. The attraction over the integrated time of the life of the universe basically suggests a mass of 10 to the 16 solar masses, which is big. It's bigger than Virgo. So to explain that, yeah, obviously that's all gravitational attraction. Galaxies are observed below, above and below. So much of this point is obscured by the galactic plane, so we can't see through it. But we can see galaxies up and down around what's called the zone of avoidance. And based on that, basically, we meaning lots of these institutions, have measured the peculiar velocities, that is, the velocities that are outside, beyond Hubble, that are large enough and coherent to reveal that there is a flow towards a point called the great attractor. The great attractor was coined by Alan Dressler at Carnegie in 1987. So the great attractor appears itself to be moving. There are other superclusters around. So from pure Newtonian dynamics, we're looking at these masses and hypothesizing how big they must be in order to give rise to the velocities that we see. What's this?
On the lower right part of the screen. Yeah.
Hmm?
I don't know.
Okay.
That's why there's question marks.
So if we look in the sky, this is the center of the great attractor, and it may be much larger than that. And you see that it lies in the middle of the galactic plane, so we really can't see what's there. All we can see is the dynamics that Ed has introduced in all the galaxies that are around here. Yeah, it's on the other, way on the other side. Yeah. Remember, the galaxy is only 30,000 light years across. We're talking about millions of years, millions of light years. Okay, here is a word. How many people have seen this word? Okay, 1, 2. So Laniakea, which in the Hawaiian language means immense heaven, is now the dominant object, which I describe as a supercluster of superclusters. Here is a 3D rendering of Laniakea. So here is Virgo. Okay, all of these large clusters of galaxies, each individual one gravitationally bound, but this object, which spans 500 million light years, contains about 100,000 galaxies, is not gravitationally bound. That's just an object which is spreading itself through the Hubble expansion, or dark energy, if you want to go that way these days. It will eventually be torn up, or we don't really know how it will finally end up. Why is this thing stopping? Okay. So Laniakea on the sky again, you can take all of those superclusters and map them, and you see that they map again in the southern hemisphere and very close to the center of this great attractor. Okay, remember the size of this object. We're able, through measuring, that you can get three-dimensional velocities, but you can get projections, and from the projections, you can do all sorts of games to determine where they're going. So this object, Laniakea, you can map streamlines. So each one of these streams is a stream of galaxy. Each dot is a galaxy. Here we are locally falling into the Virgo supercluster. We are at this point, the scale is 500 million light years. This picture, which was generated in the 1980s, before we knew where the streamlines were, essentially shows beads on strings. Each bead is a supercluster, okay, containing basically millions of galaxies, and they are gravitationally unbound, but each knot is in itself gravitationally bound. So this is and there are voids. You see this void here. The scale of this void is hundreds of millions of light years without anything in it. So the universe now appears to be a bunch of strings randomly wrapped with beads, each bead being a supercluster or a cluster dynamically bound. So we end up with this picture. This is a picture of Laniakea. Here is the streamlines to the great attractor. 100,000 galaxies across 500, half a billion light years. So each, you can see dots. Each dot is a galaxy, although when they get dense, you can't really resolve them, all flowing into this gravitational hole. And you are here. This is where you're located. The notional view of the universe, and I mean notional because we don't really know, is that we have a homogeneous distribution of Laniakea-like objects. So this is the notional universe as determined by the ants, us. Statistically uniform distribution of Laniakea size objects. But we're not finished. Now we get really to the strange things. All of that, all of those thousands and thousands of Laniakeas are inside of a black hole. We are inside of a black hole. I know that sounds strange. This argument has been made over and over again. There are a great many discussions and disagreements about what it is, but the simple argument is very simple. Okay? A black hole is defined as a certain amount of mass within a certain size. So there is a critical mass for a given size. So if you take 1 million solar masses and you put them in a few light years, you get a black hole. You get traditional black hole. Okay? But you can have a very low density black hole if the size is big enough. And the matter energy density of the observable universe is on the order of 10 to the minus 26 kilograms per cubic meter. Very small number. If you now look at the size of the universe, okay, which is on the order of 10 to the 26 meters, and the definition of a black hole is that you have a mass contained inside of this radius, you get a number which is 10 times smaller than this number. So this number, the real universe, has 10 times more mass inside of it than the definition of a black hole. The only conclusion is we live inside of a black hole. How many of you knew that? One person. Huh?
I was wondering if you can't get beyond this universe ever,
No, of course not. But
even if you could travel into.
right. But you know about dark energy. That may be something associated with a black hole. You know, what goes on inside of a black hole. But we know nothing of the physics of a black hole on the inside. You know, we can argue what goes on the outside. So all of this is unknown physics. And likely it will always be unknown. I don't see somebody coming in and figuring it out. So if you're going to give your address to somebody from outer space, you have to give it all the information. Yeah, well, Little Neck Road, Centerport, USA, Planet 3, Solar System, Orion Arm, the Galaxy, Local Group, Virgo Cluster, Virgo Supercluster, Laniakea, and we'll have to get zip codes for the Laniakea, but there are thousands of them. So I leave you with a beautiful statement by my favorite poet, Edna Millay, the greatest poet of all time, in my view. Awful weight, infinity, pressed down upon the finite me. This is from a poem about space and time. And that's it. That's the presentation.
Good. I just got to tell you, on the way here, my grandson asked me, can we go to a black hole? I said, no, there's no way we can go to a black hole.
We're inside. So you tell that to your teacher. We live inside of a black hole. And people say, well, it's a coincidence. The physics tells you what a black hole is, and we measure the density, we measure the size. We live inside of a black hole. So lots of work to be done there. From the size and the mass. So a black hole is just a certain amount of mass inside a certain size. Okay, so you can have a very small black hole. You can have, subatomic black holes by having, a mass inside a very small size, or you can have a very low density. Everybody knows that black holes are super heavy, dense objects, and they are. But if it's big enough, then the density can be very, very low. And that's the universe meets the criteria to be a black hole. Yes?
Am I right thinking that that's not a universally accepted concept?
Well, it's universally accepted that the size of the universe is the Schwarzschild radius given the density of matter. Now, even without dark matter. So you can't argue yourself away from that. So the question is, what does it mean? And nobody knows. So whether it's universally accepted, I think every scientist knows that those are the facts. What they do with them, don't know.
Well, based on that, one common way of defining a black hole is, okay, light can't escape it.
Yeah.
So with that means that light coming from anywhere in our galaxy, given an infinite amount of time, it extends out, that light can never, at some point, that light, there's enough mass to stop the photons from traveling outside of our
Well,
universe.
if the light from a galaxy inside of this black hole tries to get out, by the time it gets out, it gets pulled back in because so it can't get out. So it's all locked in together. There are theories about multi-universes, and I don't want to get into science fiction, but the physical facts that the mean density of the universe and the size of the observable universe meets the criteria to define a black hole.
So in that case, what would be the distance to the event horizon? Yes.
What would be the distance to the event horizon? On the order of the radius of the universe. Yeah. So,
Well, top of your head, do you remember what, a light year, how many astronomical units is it?
how many what?
AUs, how many, AUs is a light year, how many astronomical units? 60,000 for some reason?
For what?
A light year, how many astronomical units?
A light year is on the order of 100 astronomical units.
No, more than that,
Well, 8 minutes for one astronomical unit, right?
it's gotta be more than, somebody look it up, I had, for some reason, because I was.
8 minutes, huh? Did you?
63,240.
Okay.
60.
Yeah.
And your cloud is.
Your
one light
Oort
year
cloud
across?
is 1 light year across.
Explain what they call them streamlines.
A streamline in fluid dynamics, you know, you have airflow, and the airflow follows streamlines. So if you drop a particle, the particle will follow the streamline, and the streamlines in fluid dynamics are controlled by pressure and velocity. Here, they're controlled by gravity, but they are essentially flow lines of where the galaxies are going.
Okay, and that the curvature of that is a map over time, or is it curved like that because this is our entire sky? It looks curved.
Because there are different masses. So, you know, if there's a big mass here and a big mass here, as you're falling in, you start to go this way, and then eventually you get under the influence of a larger mass.
I see. So it's the trajectory of the local group over time?
What's that?
Is it the trajectory of the local group over time?
The local group is attached to the Virgo cluster. The Virgo cluster is moving along those flow lines.
If I understood correctly, that beyond the event horizon, a black hole gathered material into it, condensing material into the black hole. If that's true, that would contradict the fact that the universe is expanding. How do you reconcile that anomaly?
Black hole physics, it doesn't exist, you know? What goes on inside of a black hole? There have been people that have tried to, you know, use higher order physics to figure out. It's an impossible problem to solve because it's unknown physics. So you don't have a theory, you don't have physics. Now, the size of this black hole could be expanding, you know, that could be the source of dark energy. You know, there's also. Yeah. So, and, you know, gravity itself could be modified. You know, gravity doesn't work like 1/r² inside of a black hole. There's lots of room for hypothesizing, but doing science is very hard, very hard.
We have a question at home, Linda.
Hi, thank you. It's a very interesting talk. My question is sort of related to what you were just been discussing. So if the universe is expanding, as we have measured it expanding, and now dark energy is actually accelerating that expansion, won't we reach a point where we don't have the density of a black hole? And would that mean that any outside, the light would be able to expand, you know, get out instead of being trapped in the black hole? Or is that inconceivable because is the black hole the entire universe? I'm not quite, you know.
Well,
don't have
if you think of the expansion as the size of the black hole increasing, then yes, then the density will continue to drop until eventually you're not a black hole anymore. But I don't think that that's what the expansion is. The source of this expansion, the dark energy or whatever, is not known. And you can't hypothesize, in the three-dimensional physical world, we think that it is the edge of this black hole that's expanding. That's not the case. But it may be the case. For all I know, we may all of a sudden reach a point where the density drops below that critical density and we don't have a black hole anymore. But it's all unknown physics.
Okay.
Very good.
Okay? That,
Thank you.
Bravo.
Um, with NEAF coming up, just remind people at home and.
Oh.
Coming up.
I was just reminded that NEAF is coming up this Saturday and Sunday. So for those of you at home, probably most of you know it. I had forgotten, but it's 2 days and you'll want to register and pay beforehand because it's a significant savings for the 1 or 2 days. So thank you, John. Anything else we should mention? Well, thank you all for coming. This was awesome.
You're not gonna make